So folks, the plan today is to start recording 3 video segments on the buckling of composite laminates using the Catia's native FEA solver. Okay, these are very simple problems. So let me start with the content of video 1 that I'm going to be doing now. I'll put this thing in the slide mode. Okay, so the geometry under consideration is very simple. It is this strip, which is 48 inches by 12 inches, and it's made of a material, a ply, carbon epoxy ply, a single carbon epoxy ply, which is of thickness 0.25 inches. This is a huge thickness, so you can imagine that these are multiple uh, layers of carbon epoxy in the same orientation, which is 0 degrees, as you'll see, of much smaller thicknesses, and added together is going to give you 0.25 inch. Okay, so instead of doing 50 layers of 0.05, because of the nature of the problem, I can solve it because of the nature of the stacking sequence, which happens to be uh, uh, balanced, and of course this is symmetric. I can do it as a single lamina of thickness 0.25. Okay, now this is simply supported on all 4 edges, and we are applying a compressive force Nx, and we like to know what the buckling load Nx is. Now notice that here I have drawn Nx on both sides, but in reality all I needed to do was to draw one Nx, for example, at the left side you can see, and the other side, this Nx that you see there is really the reaction force, which is caused by the simple support over there. So this drawing may be misleading. I don't need Nx on both sides. One side is going to do it because the other side is simply supported, and really the reaction force is also happens to be Nx in the direction shown. Okay, now as far as the simple support is concerned, they are shown here. We will get to that later. We're going to model this thing as a single ply 0 degree. Okay, as I mentioned earlier, you could have thought about this as many plies 0 degrees, but the thickness of those plies is going to be total laminate thickness 0.25 divided by number of laminas. Okay, but that's not how I'm going to do that. Because of the fact that this stacking sequence is balanced and symmetric, I can lump them all together in a sense and solve it as a single problem. And by the way, the nature of the geometry. Okay. Now, the material properties that I'm going to be taking are taken out of the East Carolina East Carolina sequence of videos on composite materials. These are the ones. These are typical of carbon epoxy, and simple support means that the situation that we're dealing with later on when we import our composite properties, we're going to make it symmetric about that reference surface. Okay. Now this is the address, YouTube address of that particular tutorial. Now in there it shows you that the the critical uh, compressive forces are given by that expression, which incidentally, if you calculate D11, D22, etc., these are bending stiffnesses, and they and then plug in M equal to 1. That's going to be, you're going to get a particular critical value. These are all in pound force per inch, which incidentally is pounds, because no, if you want to actually want to know what the load is, you multiply by 12, because the width of this is 12 inches. But anyway, these are the theoretical values derived in that website. Okay, that video, very straightforward. This formula you can find in many places. But anyway, we're going to check our numbers against these. Now notice that here, the smallest nx happens with the value of m being 2, which means it's this 1,217 Newton per inch. Okay, this M means M equal to, in our case, M equal to 2. Okay, now let's not worry about this thing. We're going to put this thing here on the side later. But I also wanted to remind you that this this Catia run was done with V5-6R 2018. And if you do it with the other releases of Catia, dialog boxes may be a little bit different. And unfortunately, there are situations where there were also some bugs in displaying stresses, particularly components of stress in other releases of Catia, which have been corrected to a great extent in this version. Okay, good. So let's put this thing on the side here. Now, first thing we're going to do is to create my material properties, because these are not standard stuff. So we go to Start, and we go to Infrastructure, Material Library. We double click on this and we give it a name. So I'll say carbon, how about doing it like this? Buckling underscore simply supported carbon epoxy. Carbon epoxy. Epoxy. And I will also give it a thickness of 0.25 inches. Okay, so that's the name that we give it right there. It's a very long name. Now for composite, we click on the composite tab, and for the skewed thickness, I'll make it 0.25, and this is unidirectional. Apply. And then we click on the analysis tab. We're going to change this thing to 2D orthotropic, and we put in our properties. So that's going to be 20 million e to the 6. That's a longitudinal Young's modulus. This is 1.2 e to the 6. Transverse. Poisson ratio is 0.25. Shear modulus in the XY plane is 800,000 psi. 1, 2, 3. And for the other two planes, I will make 400,000. 3 and 4, 0, 0, 1, 2, 3. Okay, we don't need anything else, so we say okay. Let's check it here. Let me move this thing on the side. Check it one more time. And the reason I check it is sometimes when you do this, that thing changes inadvertently, or I don't know, for some reason, sometimes I do this and I think it's okay and I check it. It's not orthotropic material. It says isotropic and stuff are left out. Catia will not run and everybody gets upset. Okay, say okay. Now save this thing. So I do it from here. I'm going to put it in that folder on my desktop, buckling, single ply, carbon epoxy right there. And I will give this thing a different name that I can identify with. So how about January, today is the 5th, January 5th. January 5th, 2021. Excellent. So we save it and we close this. Now we're going to create our part file, which is a simple surface part. Okay, so on that horizontal plane, I will sketch a rectangle which is 12 inches by 48 inches. Mention this thing. So this is, let me do the other one first. This one is 12. Okay, and the one on the top is 48. So this is actually horizontal strip, 48. There we are. We're done here. Why don't we fit it so that we know what we have done? Right there, exit. And then we fill it, F-I-L-L, to create a surface. And then I join it The purpose of the join is for me to have a control over the direction of the normal to my shell elements that I'm going to be using. Double click on the join, flip the arrow so that the positive direction of this join is down, which means the elements that are going to be created meshing the surface are all going to have a normal to the normal, which is opposite to the direction of the joint. Okay, not a critical step. Now we're going to create a axis system here that we're going to it's going to be used as a rosette. So click on the axis system right there. See this? Create a point. It did create it here, but I don't like it to be located there. I want it a little bit to the left so that I can distinguish my coordinate system. So how about doing a minus, I don't know, 12 there. So it's going to put it at that location. And I'm happy with this, except that I'm going to uncheck the current so that this is not used as the global origin, basically. The global origin is where it was right there at that location. All right. So save this thing. File, save management, save as, desktop in this folder. That is correct. Very good. Okay, now we're going to go to Composite Design Workbench. This thing, I personalize it so it appears on the top, but if you're looking for a mechanical design, right there, composite design. Okay, good. Now, the first thing that you have to do, notice that most of these things are dimmed, because the first thing that you need to do is defining composite parameters. You click on it, add material. Remember, I created that material property. Let's go get it. It was on the desktop. Where was it? Buckling load right there. January 5, 2021. Okay. And we say okay. And it's put in there. Here's my cube thickness, 0.25, right? Now, for rosette, this is add a rosette. You select this coordinate system and you hide it. You don't need to see that. Say okay. And the direction that we want is zero. It's already there. We don't have to worry about it. Okay, so right there. Now this is a very simple ply, so I'm going to create it manually. So first you have to define the plies group right there, ply group. Surface is right there. Flip the arrow so that I always have a habit of draping in the upward direction. And the rosette is automatically fixed, and lock plies draping direction, which is fine. There's only one of them. Okay. So we created the plies group. Now we're going to create our single ply right there. See this? Right there. And it's waiting for you. If you look at the bottom left corner of the screen, it says select ply group or sequence or ply to create ply. Okay, well, obviously this is what it's saying. Select this. As far as the boundary of the ply is concerned, it's that sketch. We can select that sketch. It's very simple. It's this purple one, magenta one. As far as the attributes, it's this material, and the ply direction is, or fiber direction is 0. Okay, I don't have to change. This is already default. Good. Now you can always look at it if you want. So if you click on the apply exploder and you select the ply group and say apply, it's right there, a single ply. Cancel. Don't need it. So we save this. Okay. So now we're going to go to uh, advanced machine tools, because I want to use a nice rectangular type element. And we click on this is okay. We click on the surface measure right there, surface measure. You select this. And I want to remind you again that this arrow tells you the direction of the normal to the shell elements that is going to be covering the surface. Now it's upward because it's opposite to the direction of the joint, which excuse me, which I flipped so that it goes down. 1 inch is good because remember this is 48 by 12. I don't want to put a small number there. 1 inch is good, and we say okay, and we zap it or mesh it right there. See this? Mesh it, mesh the part. We say okay, and we exit. So it's already meshed, but to see the mesh, I'd rather go to the generative structure analysis and put the cursor on the nodes and elements, right click mesh visualization, and change the rendering down here to with edges. So this is what we got. Basically, it's 12 by 48. It's about I don't know, 500-600 nodes, elements. Okay. We now hide the. I don't want to hide it, but I'm going to deactivate it. Okay. Same thing. We can also delete it if you want. Now, deleting the mesh does not mean the mesh is deleted. It's just that the visualization, the plot of it is not shown, deleted. Okay, so what we need to do is, let me see now. What about importing the composite property? Import composite properties. It's that surface, support is that surface, and we're going to do it by the plies. So we have to select the ply group, which is in our tree. So you have to expand the tree, expand under stacking, select the ply group, okay, and make sure this box is checked. It's as if this 0.25 inch thick thing was 0.125 above, 0.125 below. Okay, now we're going to apply our restraints. So one thing we want to do is we want to hide the ply, because notice that when you put the cursor here, look what's picked up. See, when you put the cursor on the edge, ply groups is picked up. So why don't we hide this? Also, there's another thing here. When you put the cursor here, the sketch is picked up. See that? When you put the cursor on the edge, the sketch is picked up. And we want to hide this thing because you cannot put loads and restraints on geometrical entities, and both the sketch and that uh, the ply contours were geometric entities. Now when I put the cursor on these sides, only the edges are picked. See that? Only the edge. It's not the whole thing. It's not the sketch. Okay, so let's apply our restraint. So first of all, a user-defined restraint on this edge, and I want to guide you to this video segment, to this here. On the edge x equal to 0, uz and ux are 0, okay? So we go there, uz and ux. So translation 1 and translation 3 are 0, okay? On this edge, because we are pushing it in the x direction by force, x should be free, okay? So you click on this, x is free, but z is fixed. It cannot just come out of the plane. And on these two edges, on the side edges, let me guide you here, on y equal to 0 and y equal to 12, uz and uy are 0, okay? So we do this, we select this edge, and we select that edge on the other side, uz and uy are 0. Ux is free because as you compress this, you push this thing, it can compress, it can move in the x direction, things can move in the x direction. Okay, good. Let's save the analysis. So file, save management, analysis, save as, right folder, analysis 1, and we say okay. Now, the way you do buckling in CATIA is first you have to do a static analysis. In other words, first I'm going to apply a load here in the negative direction. Of course, the load on the edge must be pound force per inch, for example. So we're going to be using right there. So line force density. So on that edge, I'm going to put -1 LBF underscore IN, which automatically it converts it to this 175.1 Newton per meter. And if you ask me, well, why don't you change the units so that you don't have to? It doesn't convert it into that. Well, I could not find the units of line force density. I just couldn't find it. Okay. So we say okay. Notice that the direction also minus means that it is compressive. Now, so first you have to do a static analysis. There's no way around it. So you run this thing. And assuming that nothing is wrong, nothing else is wrong, you run it. Okay, it did run. Let's plot the deformation. It looks like that. Nothing surprising. Nothing surprising. When you compress on that, we expect it to shrink. You can see that right there. You can see. You can animate it and see what happens. Now, So then you insert a buckling analysis. So you put the cursor there, insert buckling case. So remember, first you have to do static case, we did it. Then you do buckling case, and it's asking you, where is that static case that you did? Because it could be that you do several static cases, not in our situation, but several, and then you have to go and say, which I want to do buckling on which one. In this case, there's only a single one. The only thing that we can pick, the only thing in the tree that we can pick, look, nothing can be picked. You expand the static case. The only thing you can pick is right here, right there. This is the static case that we did, right there. You select it, it takes it as a reference. That's it, and then you run it. Notice that it did add a buckling case down here. It did add a buckling case. It's using that static case solution as reference, and then you run it. If you say all, it will run the static case again, which is not necessary, but that's okay. Done. So, what do you want to see? You want to see the deformation. You want to see the deformation of the buckled structure. You click on it right there. So here's what we're going to do, not there. Expand this. Double click. See, this is the buckling case solution. We created that image for it. Double click on it. Occurrences, these are the different buckling loads, okay? So what that means is that take the force that you had before, take the nx, which we said is equal to -1. Do you remember that? Multiply it by this, and you're going to get a buckled force value, force per unit length value in this shape, okay? And if you go here, take that one that you took as load, -1 really, and multiply it by 14.6.8. This is the buckling factor, and that is going to be nx of a buckling load, third buckling mode, like that, okay, etc. Now, if you compare this with the reference values that you got, let me minimize this, move it on the side. I'll put these things side by side. Okay, so let me make this thing bigger. Okay, so look at this. This one with two lumps, in other words, m equal to 2, two half signs. Two half signs is actually, it's right here. See this? It's right there. Okay, right there. If you select the next one, it's going to be higher load. It's going to be a higher load. It's going to 3. And what is it? 1468. So you go to this list. 1468, third one, right there. It's approximately 1538. These two kind of match, okay? If you go to the third one, uh, what I'm going to do is, in the next video segment, I'm going to take this uh, this particular carbon epoxy lamina. I'm going to split it into two, so each one is going to have 0.125, and use it as a skin in order to take a core, a foam core, a foam core, high density foam core, and cover the top and the bottom of the skin and calculate the buckling load. Okay, folks, good luck.